Let's do a math problem. This is a problem that came up in class. We were doing the divergence theorem. We needed to calculate the flux over the whole this wedge that I came up with. I don't even know where I got the problem. I probably got it from somewhere. And most of the surfaces have a zero flux because of this weird function. But I just want to do this angle piece. I want to calculate the flux on this this side of the wedge. And I'm going to do it I'm going to do it two ways. I'm going to do it two ways, right? I'm going to do it on paper, and then I'm going to do it in Python just to see if we get the same thing, because you never know if you're going to make a mistake. So I have the function xyz, xyz, xyz. This is my force or field, whatever you want to think of it. And I want to calculate the flux over this surface, which is just the f dot n hat dA, the integral of that over that surface area. Okay, so we got a bunch of stuff to do. Number one, what's in hat? What's in hat for the surface? In hat should be pointing away from that surface. Well, there's a couple ways to calculate that. You could kind of just guess it if you wanted to, but I don't like to guess things. So instead, what I'm going to do is to say use the cross product to find in hat, right? So if I know two vectors in this surface, then I can find the cross product of those two vectors, and then I can use that cross product to find the unit vector in hat. So let's take this vector A from here. So I'm going to say A is going to be equal to the vector 0, 0, 1, 1, right? That's in the z direction. And then this vector right here, and then A cross B, I'll call that B. A cross B is going to be equal to the direction of A cross B is going to be in that direction. So B is the vector from here down to there. So I'm going to write this as, it goes 2 in the x direction, -1, 0. Now I'm going to take the cross product, A cross B. It's going to be the determinant of the matrix x hat, y hat, z hat, 0, 0, 1, 2, -1, 0. When I take the determinant of that, the x hat component, I get 0 times 0 minus 1 times -1, which is going to be 1. And then the y direction is going to be 2 minus 0, 2. And then in the z direction, it should be 0. Yeah. Now, that's all fine and everything, but that's not a unit vector, right? So I need to find the magnitude of that. So the magnitude, so I'm going to, we can do that, right? That's just going to be 1 squared plus 4 square rooted or square root of 5. So if I can say n hat is going to be 1 over the square root of 5 times 1, 2, 0. So that's important. Now I can do f dot n hat because that's just a scalar function. So f dot n hat is going to be this dot 1, and I have the 1 over the square root of 5 still, so I'll put 1 over the square root of 5. And then I have 1 times that, x, y, z. And then I have plus 2 times that, that's plus 2 times x, y, z. So that's a parentheses. I don't know why I'm thinking about vectors. And so then putting this all together, I get f dot n hat is 1. Well, and then I get 1 plus 2, so I get 3 over the square root of 5, x, y, z. So that's the function I want to integrate over that surface. Now, how do I break this up into pieces? Well, if I know the function and it has x, y, z, the area element, I can just take a little area element right here, like there's a little square, and I can project that down into the xz plane. See that? And then I can just integrate over the xz plane because it has the same area, projected area as that wedge. So here's a side view. Let me put my function before I forget. F dot n hat is going to be equal to 3 over the square root of 5 x, y, z. Okay. And then on the side, I have this, which you can't even see. Weird. Okay. That's y. That's x. I'm looking at this from the side like this, and I'm projecting that down. So this area element, dA, is actually equal to dx dz. And then I'm going to integrate from x equals 0 to 2 and z is 0 to 1, right? Because this is a 2. I didn't draw that quite correctly, but that's fine. So I can write my integral now. Phi 1, the flux, is going to be the integral, the double integral, and let's do z first. Z is equal to 0, from 0 to 1. My notes, I have 2. I think it's 0 to 1. 0 to 1, x equals 0 to 2. Yeah, I'm pretty sure that is. And then my function, 3 over the square root of 5, x, y, z, dx, dz. But you see that we have a problem here, right? Because I have x, I can integrate x. I have z, I can integrate z. But what about y? Well, now that's where we have to use this function up here to determine the value of y. And so if I look at that from the side, I can see that y does depend on x. And we have the equation, we have a straight line right here. So I can say y is equal to the slope of this line, which is negative 1/2 times x plus 1. That's the slope. You can do that slope if you want, right? It goes down 1 over 2, so the slope's negative 1/2. And then in order to make this 1 right there, x equals 0, I put 1, so the y-intercept's 1. So I can substitute that in right there, and I get the following. X is 0 to 2, z is 0 to 1, 3 over the square root of 5, x, let's leave that up, times negative 1/2 x plus 1 z dx dz. Let's do the x integral first. I don't know why. I did it before I did the x integral first, but I'm going to multiply this out. So this is going to be the double integral of 3 over the square root of 5. I have negative 1/2 x squared plus x. And then there's a z in there too. Z. Yeah. dx dz. So let's integrate the x. If I do that, I can treat the z's as constant, and I get phi 1 is going to be the integral z equals 0 to 1 of this stuff. So if I integrate x squared, I'm going to get x cubed over 3. So I have 3 over the square root of 5, x squared, x cubed negative, x cubed over 6, right, because I already had a 2, z, there was a z there, and then I have an xz, so I get plus x squared over 2z, and I have to evaluate that from 0 to 2, and then I integrate in the dz direction. Okay, so let's multiply this stuff in, because I get this 3 is going to cancel right there. I have the 1 over the square root of 5. I'm going to leave that out front. That's obviously not going to cancel with anything. 1 over the square root of 5. So I have, if I put in, I'm going to do this all in one step, which I shouldn't do. If I put this in, if I put 2, I get negative 2 cubed is 8. And then I divide by 2, right? I have divide by 3. I'm getting negative 8. Yeah, negative 4z. Negative 4z. And then I evaluated that 0 is going to be 0. And then right here, I get 4 over 2 times 3, which is going to be 6. Z. And this is still, I still have the integral. Z equals 0 to 1. Okay, so now we got one more integral. Let's do it. I get 1 over the square root of 5. This is pretty easy. I get negative 4z squared over 2. Oh, I can add those two together, couldn't I? No, wait. Yeah, that's fine. Plus 6z squared over 2 from 0 to 1. So this is going to be 2, negative 2, and this is going to be 3. So I get those 3 plus negative 2 is 1. So I get 1 over the square root of 5. Done. And that's phi 1. I was trying to do that without going to the next page. Okay, so now this is one of those cases where like I easily could have made a mistake, and I don't know that's legitimate. So what I want to do is to break this into to points, right, and do it numerically. So imagine that I have my surface right here. I'm going to break this into a bunch of little pieces, and each one of those pieces I'll calculate the flux because the function changes over space, and then I can just add up the size of all the pieces. And it's just for fun, really. So, I mean, it's kind of not fun, but it's serious too, but it's also fun. So let's switch over here to Python. I have a Python thing pulled up. The first thing I want to do is to define my function as a function. So let's define f as a function. So def f, I'm going to pass it some vector. I'll call that vector that I pass it ROT, right, for temporary, ROT for temporary observation locations. I'm going to pass it a vector, and it's going to return me a vector force, XYZ, XYZ, XYZ. So that's pretty easy. I can do this all in one step. Let's just have it return. I want this a little bit bigger. Return the vector rot.x times rot.y times rot.z. Right, so rot.x is the x component of my observation location. So that is x. Rot.y is the y component. Rotz is the z component. So that's my x component of my return vector. And then the y and the z are going to be the same thing. And that's that. Oops, I don't want that. I messed up. I missed a parentheses. Okay. So let's just test it just to make sure it's working. Print f of vector 1, 1, 1. Okay, so that makes sense. 1 times 1 times 1 is 1, so that's what we should get. Okay, got it. Now I want to find my unit vector in hat. And I know I already did that, but I'm going to do it again, right? So I know I have the vector A is equal to the vector 0, 0, 1. I know B is equal to the vector 2, negative 1, 0. So let's call in hat this. Norm cross AB. So cross AB is a built-in Python function that returns the cross product of A cross B. But then I need to make that a unit vector, so norm returns the unit vector for a vector. So this cross AB gives me a vector, and then I take norm and it gives me a unit vector. Let's just print that. Print in hat, just to see that it does work. Okay, so there's my unit vector, and this is off a little bit. It's weird. Okay, that's good. That's off. So that's my unit vector in hat. I don't really need to know that. Now what I want to do is to break my surface into, let's say, 100 points. And I'm going to use random points over the surface. Why am I using random points? 1, it's fun. 2, it's an easy way to kind of distribute those points. Yes, I could make a double loop and kind of loop over there and make exact squares. But it's kind of fun to do this with a Monte Carlo calculation using random numbers. And so that's what I'm going to do. So let's do this. N equals 100. Okay, that's how many points I want to make. And then I'm going to set n equals to 0. So capital N is my total. Lowercase n is my counter. That's the way I like to do it. Now, I need to find the area of each one of those pieces. So let's say this. A total is equal to, the area of that piece is 2 by 1. So it's 2, right? So now the area of each piece is going to be, I'll call it dA, is AT divided by N. So if I'm going to break it into 100 pieces, each piece has to have an area of 2 over 100, if that makes sense. Okay. So I'm not going to use that in a little bit. Let's just make our pieces, and we'll go back and calculate the flux. So how do we make pieces that are in that wedge shape right there? Well, the first is this idea of using random. Random is a function that returns a number between 0 and 1. So let's just run this. So print a random number. Random. Do it again. Different random number. Okay. So I can use that to kind of make a space. Now, I want to make a uniform space in the XYZ direction. So I'm going to make a box of points that goes from x equals 0 to x equals 2, y equals 0 to y equals 2, z equals 0 to z equals 2. So sometimes you can kind of make it look a little bit better and not go 0 to 2, but when in doubt, make everything equally distributed. So let's make 100 spheres. I'm going to draw them, spheres in a box, 0 to 2, 0 to 2, 0 to 2. So I can do this with while n is less than n. Now I'm going to calculate a random vector. I'm going to call it RT, and it's going to be vector 2 times random. That's going to give me a number between 0 and 2. 2 times random, 0 and 2. 2 times random, 0 and 2. And then what I'm going to do is take that random number, I'm going to put a sphere there. So sphere, I just need the position is going to be that vector. And then the radius, I just pick, let's pick 0.1. I don't know if that's too big or too small. And then I'm going to add 1 to my n counter. And so I should get 100 points in a 2 by 2 by 2 box. There you go. That's 100. You can count them. 100. They're a little big. Let's say, put this at 0.03. Okay. Now what I want to do is to start cutting things away. And then I can increase my value of n. So the best way is to cut things away. To do that, what I want to do is to take my random variable, and if it's greater than z equals 1, just throw it away. Okay. So there's my random variable. I can say if rt.z is greater than is less than 1, I'm going to keep it. How about that? So then I'm going to make a sphere, and then I'm going to make add 1 to my point. So if it's greater than z is 1, just throw it away. And let's do the same thing for rt.y. I want those less than 1. So I'm going to kind of squish it down. I'll get a box that goes 1 by 1 by 2. So there's my box, and now you can see it's 1 by 1 by 2, right there. It doesn't always look like a box. It's only 100 points. It's not that many. Okay, yes, I'll do it for 1,000 just once. 1,000. There. Now it looks like a box. Okay. Now what do I need to do? Okay. Now I need to kind of limit the points only in the surface of that plane. That's what I want to do. And then I can use each one of those points as an area. Now, I can't say y equals negative 0.5x plus 1 and say only if it's that value. I could do it, but I may never actually get those values. So in fact, I want to give it some thickness, right? I want to give it some amount of thickness so that I can get some volume in there. And so we just have to pick. So I'm going to do this by saying, there's my conditions for the y and z direction. And I'm just going to say, and rt.y is greater than negative 0.5 times rt.x plus, not 1, but I'm going to say 0.99. And rt.y is less than negative 0.5 times rt.x plus 1.01, right? So now I put my boundaries. So instead of being up and down like that at an exact point, I have some thickness. Okay, so I didn't even do anything yet. I'm just going to run it and let's see if we get these points in a wedge. I did it. I mean, it's always kind of amazing that works. You know, there I have my wedge of 1,000 points. Now what I need to do is just go through each one of those points, pretend like they're in an area. I know n hat, I know dA, I calculate the flux for each piece, and then add it all up. That's it. Let's do that. Okay, so here we go. I need a flux phi equals 0. If I'm going to add flux to something, I need to start with something. And then down here, when I have my points, I'm going to calculate the flux. D flux is just going to be f of rt. It's going to be the dot product, dot f of rt n hat. That's exactly what the equation says, right? And then I need to multiply that by dA. That's it. Now I'm going to add my phi. Phi equals phi plus d phi. And that's it. And then print it out. Print phi equals phi. And let's run it. Okay, so is that right? Well, maybe I should print out the theoretical. Print phi t equals 1 divided by the square root of 5. Check that out. And it's always nice when it works, right? So this is I like this Monte Carlo calculation because we can make this this wedge face numerically and just break it into a bunch of points, and it's kind of fun to do it that way. So, okay, the link to this code is down below. Hope you find that useful, and that's that. Talk to you later.